Oh, no, I think the other.
I mean, this one is not.
That's bright enough for me.
No,
I mean, so like colorblind people. Can, yeah.
So you're colorblind?
It's not colorblind, but color deficient.
So this is okay. I think.
Using the T is good. Yeah, maybe.
Yeah, so people say red laser pointers are now colorblind.
I mean, I think the neutrino background.
The things that are for higher energy blinders.
No.
Yeah.
They go this way.
They wobble. They have the idea.
I don't know. I don't know whether the K of the intense outside.
Yeah, outside. Yes. Yeah. It's for the like general public.
It becomes a radiation hazard.
Well, potentially.
Right.
If you stick a few meters on the ground,
Oh, I
it's
see.
okay.
Okay, so you point
For like
Oh,
and then that they don't also
you can say the cost you can.
Wobbling, then it's below whatever's well below the legal limit.
Okay.
They have some number of microsieverts.
Hi, Venice.
Remind me of your
Roger. Nice to meet you.
Roger. Oh, yeah.
Yeah, from years and years ago.
Maybe I'll come over here and check.
Hey, how are you? APS strategy. Or a pre strategy.
Let's get your tea.
I might be. I love what you've got here.
There's always.
It's gonna be raining for the weekend, but it came early in the whole.
You've got the nice weather. Unseasonably.
It's all very cheap. But here we need to do.
What have you been up to? What?
CMS. Higgs.
Oh, you can hide it.
Answer detection.
Yeah.
Intersection.
Hide
The ones with the shortcut. Lower. 4 more. Two more. No, 2 more.
High floating meeting control.
4D tracking.
Yeah. Up. Yeah.
5D
Down.
Yeah.
So I'm trying to go to the next level and turn reference close to the reference.
Yeah. Yes.
Yeah, so some of them went upstairs. Is that all set?
Can you see? Oh, sorry.
Okay, I can see some.
Or maybe we can use audio.
Okay. Okay, great. Hello everyone, welcome to our special seminar today. It's a sunny Friday afternoon. Today we're really happy to have Professor Cao Han from University of
on the way. And then once we're here, we can do this. There you go.
Yeah, so I'm going to there's an echo. Okay, yeah. So I'm going to discuss some of the recent work I have been working and thinking. In fact, including some of the early works, it's maybe even almost like 10 years from the early work. So of course, this has some recent interesting application for this the high energy lepton collider, such as muon collider. But when we started thinking about this physics, it was even before the muon collider, before the high energy muon collider was brought up. So the topics include some relatively theoretical considerations, but in particular within the standard model. So this electroweak physics, here you will see that many interesting aspects I hope to convey to you and convince you it's interesting. In fact, I recall that Jen said I was at a Fermilab as postdoc. So I was talking to Chris Quick, and Chris Quick, of course, the prominent theorist, many of you know. And Chris told me that when he was young, there was also such time that everybody was young. So then Chris was young, he was asking Ben Lee. So he asked Ben Lee. Ben Lee, of course, was a prominent theorist as one of the, I think, the first theory group leader at Fermilab in the 60s. So Chris Quick was asking Ben Lee what may be interesting to work on. Ben Lee said weak interactions at high energy. I think that remains to be true. So we continue to learn more about weak interactions. Of course, that collaboration was very fruitful. That led to that famous paper to lay out the Higgs mass bond and unitarity bond at very high energies. So you will see that that kind of aspect remains to be true, that we have not really reached completed that level yet in terms of our deep understanding within the standard model. So the issues include some kind of a QCD like a splitting phenomena, which turn out to be dominant phenomena at high energies. And also you want to play with the longitudinal gate bosons and Goldstone-boson equivalent, so-called Goldstone-boson Equivalence Theorem, and all these things come in and at extremely high energies. But unfortunately, we seem to have some new ideas to take us to the high energy regimes, multi-TeV, order of 10 TeV region, and that took place in the rather recent years. That is my second part of the talk, to give you some flavor that what kind of the high energy electric physics may show up at multi-TeV colliders, which is also applicable to the so-called FCC, the version that the CERN has been proposing. They called the Future Circular Collider, FCC. That's the CERN's version. There's another proposal in China called the SPPC. It's a super proton collider. It's a hadron collider, presumably almost increase LIC energy by order of magnitude, in fact, a factor of 7, and to reach order of 100 TeV center mass energy. And some of the discussions in terms of physics are also equally applicable to that. In fact, they're also applicable to some extremely high energy cosmic rays. But of course, those things are there I would not comment on, because this recent excitement for the possible multi-TeV muon collider is very interesting. It generates a lot of interest in our community, in particular among our junior colleagues. So that would be the example I want to show you, but only take that as an example. But because of time, I think here I probably will be rather sketchy and rather quick. But if you are interested, I'm happy to discuss with you more details. Fortunately, I have the local expert, Jen, has been working on this as well. If you have some suggestions, comments, and I'm sure the Jen will be happy to discuss with you. So that's these two parts basically. So let's start from this the high energy electroweak. What is the electroweak in terms of the high energy? So basically, we have an order parameter in terms of the condensed matter language. We have this so-called vacuum expectation value that generates, as we know, in the Higgs sector, this vacuum expectation value generates all the elementary particle masses. Okay, presumably all these elementary particles get their mass from this same vacuum expectation value as the Higgs condensation. Let's look at the numbers. So of course, at the early time, ever since beta decay was observed, discovered, we simply parameterize this the Fermi constant, G Fermi times the available energy. It's the MEV range. if you think about the low energy around the nuclear physics, MeV range, and this is a very small number. This is why we call that weak interaction. In fact, in terms of coupling strength, it's the same as electromagnetic. But the reason it's weak is that we are really probing the energy regime, the physics, much below the electroweak scale. That is the real reason why it's weak. However, it doesn't have to be always like that. If you think about the higher energy colliders around us, LHC is a few hundred GeV easily, right? So if you move on, and then this number is scaled up. But if you move on to the future collider, multi-TeV collider, and this is a huge number. So this is not a useless number. The reason is that the longitudinal gauge boson, which is the Higgs counterpart, that part behaves differently from the gauge field, like photons and gluons. That part is an additional massive component of this vector state, and it comes from the additional degree freedom. So of course we call that the equivalent theorem. I will comment on that later. But nevertheless, this behaves differently from the pure gauge interaction. That behavior sometimes is called bad high energy behavior, because it's very high energy with the wave function. The longitudinal gauge boson wave function behaves a lot. So therefore, it's very conceivable to reach the extremely high energy physical regime because of the additional degree of freedom as well. It's beyond some simple electromagnetism and so on and so forth. Let's turn this other way around. Think about this other way. If you think we are reaching high energy scale, and in comparison with this vacuum expectation value around us, this is the Higgs vacuum expectation value, all the particles around this, all the heavy particles around this mass, WC and the top quark and Higgs boson itself. If you think about that, so the 10 TeV is really critically important. The 10 TeV is really the regime. We go beyond WC top quark mass. And you think that this vacuum expectation value is huge, 250 GeV, but if you go back to think about QCD. QCD here is a same number, but with the 3 orders of magnitude below, the few hundred MeV. So therefore, the electroweak scale is as light, as small as a QCD at 10 TeV. 10 GeV is pretty big energy at for QCD. That's why you start producing jets already. So a few GeV region, that's a jets observed. And in fact, you can even argue that the fact you see the jets, the gluon jets and quark jets, that is indication you are in a new different regime. This is in the so-called the symmetry restoration regime. And in our real world, we don't see quarks, we don't see the gluons, we only see pions, kaons. That is a different phase, broken phase. We are living in a broken phase. If you go to a higher energy, this is the energy that you open to restore the QCD already. QCD is fundamental degree of freedom change from your pions, kaons, and nucleons to the quarks and gluons. So therefore, I think it's quite interesting to reach the regime that is similar to the QCD case, and we can explore what may or may not happen in that regime. So it's going to be very sensitive to any new physics in that regime, maybe even physics beyond standard model. So therefore, I think the thinking about the high energy physics for the electric sector remains to be as interesting as in the 70s and 80s that Chris Crick and our colleagues set up is the electric physics and Higgs search and so on and so forth. So therefore, if you think this is so much bigger than the QCD, than the lambda QCD, and the vacuum expectation value is small. In that case, all the particles in the QCD language, the normal quarks, they are pretty much massless. So therefore, in this energy regime, all this electric symmetry breaking scale is small. So the top quark mass is small, W mass, anything proportional to vacuum expectation value is small. This is the regime we may explore approximately is massless theory. And therefore the electric symmetry is restored to some extent. You have a pure gauge theory, just like isotropic cross U1, massless, and also you have the scalar sector. It's largely massless as well in terms of numerics. I think this is an interesting regime to think carefully. And the first part of the talk, I would want to hope to convince you there are many things that in this regime that we still need to learn. We even don't really know very much yet. So this is what I said here already. This V over E is small, and you need to you do the proper power counting here. That power counting basically did not exist in QCD. We dropped them all. lambda QCD is small. Lambda QCD, any power suppression is always small. If this power correction is large, we get into the non-perturbative region. Now we cannot handle this anymore. We can handle this orbital lattice or whatever in this when this the power counting is significant. So we only consider logarithmic large Q square enhancement. The power counting is important. In QCD, it's called higher twist. Higher twist effects. It's a non-perturbative that we don't have a proper theoretical mathematical treatment anymore. But here, the electric sector is like QCD to have this power counting property. And hopefully we see some kind of different phenomena. We call it different phases, the symmetric phase and the broken phase. Of course, we live in the broken phase, everything is massive. But unlike QCD, QCD part, once you get into this so-called higher twist non-perturbative regime, you need a different treatment, such as a lattice gate theory, whatever. But in the electric theory, you have to count this properly because this will define a perturbative regime. Even below the electric symmetry Brinker scale around us, we need to treat this properly. It will define a perturbative theory. So in a sense, even this there's a phase transition after after Higgs field develops the vacuum expectation value. That phase transition is from symmetric phase to the Higgs phase. The Higgs phase does not present the same like QCD the confinement. We don't have the same confinement. So the physics is quite interesting, similar but very different. So that's another reason I think it's interesting to continue on. But I will be quick about here. This is more numerics. So if you think about the multi-TeV collider, the at top 120 TeV, 170 GeV or so versus your center mass energy, it is similar to MB versus 2 TeV. So top quark is as light as bottom quark at the heavitron. Okay, top quark is as light at this energy regime as the bottom quark. Remember at the heavitron time, there will be a lot of theoretical arguments. Should we treat the bottom quark massive or massless as a parton? Or we should take this as just the gluon splitting production. Of course, so turn out take the bottom quark as a parton is better description in terms of the, I will comment on the resummation and so on and so forth. So therefore, it is conceivable when you go to the multi-TeV regime, all the particles so light in top quark will behave like parton. Later, I will show you that everything actually is a parton at its high energy, dynamically generated. So even inside the lepton, highly energetic muon, highly energetic electron would generate radiatively all the particles. Everything actually is parton by this evolution. So that is an interesting idea. So there's some formulation about this one too. So I will not get into that, but conceptually that's interesting. And the reason you call this parton is that besides the standard coupling, there's the logarithmic enhancement for the higher energy regime versus your light formula light quark. So therefore, if this the log is large enough to enhance your coupling, and this is not a very small perturbative quantity anymore, you need to add all these the finite contributions up. This is called the resummation. You need to resum this log enhancement to arbitrary order, because each term is not as small as coupling. Coupling is small, but there's a collinear large log enhancement. So this is why when we do the parton distribution function, you need to do resummation. You do the fragmentation, you need to resummation, and so on and so forth. So this is the case. I quickly estimate the number. If you think this delta is order for 20–30%, therefore you don't want to miss them, you want to resum, and you will have a small coupling. And then this Q square is order of TeV, few TeV is relevant already. If we are thinking about the next generation, at the LHC is marginal, it's not very sensitive. That's perfectly okay not to do what I have been talking about. Top quark is heavy, top quark is not parton. But if you go to almost like one order magnitude higher, like the future FCC, or the muon collider 10 TeV, 14 TeV muon collider we have been talking about, these things will become relevant numerically even. Okay, so this is one of the examples. The other example is similar. And the electric logs will become sizable here. In particular, if you consider both collinear and infrared, so it's the double log. We usually call this Sudokov double log. So the Sudokov double log may be significant. So therefore, you probably want to consider this the resum result here as well. Pseudo-Coff double log usually give you exponential kind of a suppression, but real emission, real photon, real gate boson emission give you the collinear enhancement. So you have to play this both property that we have been doing for the past several years. I think we have made significant progress along this line, but by the end of this part one, I want to tell you that it's even not done, even in terms of formalism, in terms of some concepts, it's not completely done yet. So let me continue on this. This is also cute. So in QCD, we're thinking about the gluon radiation under the ISO3, so the ISO3 color. But here we are talking about the gate boson radiation WZ and ISO2. But the gate radiation has a color factor. We call this the 3 gate boson coupling and so on and so forth. And here is the fermionic radiation. So CF is a fermion color factor. And here this is a CA is the gate boson color factor. If you calculate the ratio of the gate radiation versus the fermionic radiation, and this the formula N is SUN. But for QCD, it's about slightly a little bit above half. But for the electroweak, this is almost like a 3. So this is bigger. That means that if you purely think about the splitting effects, the gate boson splitting effect, ISO2 is significantly more important than ISO3. That's also interesting. It just happened to be the numerics. ISO2 gate radiation, gate splitting is relatively more significant than the QCD radiation that we have been dealing with all the time. So ISO3 radiation is very well established, even measured with our LIC data, right, to good precision. So here, once again, the quick formalism. What you want to do is to consider the collinear dominance. The collinear behavior dominance is largely because of the gated theory. I will show you that the new behavior emerges. That is from the Higgs sector. Okay. So we say we parameterize this into a factorized form. One is a splitting, and one is a splitting probability. You times the splitting probability for particle A into B and C, and multiply by the kind of a sub-process cross-section, and that is the total process. This is the final stage radiation, and with the showering, and so this is the initial radiation like a parton distribution function, but it's a similar formula. But these formulas need to be proven. At this level is our assumption, so you need to prove this to have these finite, well-defined factors. You cannot have a divergence in one with the other, then you lose your predictivity. So you need to show that each factor is individually finite, well-defined, and this factorization works. And I want to argue that in QCD, this is proven for certain processes. Most of the processes we measure, and most of the observables we define in the electroweak is to a somewhat even lesser extent. So I'll come to that reason why this is so. Again, this is what we use all the time. But from theoretical viewpoint, if you do this order by order to a higher order, this need to be proven order by order. Otherwise, this is just an assumption. If one of them is divergent, like infrared divergence or collinear divergence, and then this formula actually is ill-defined. Again, this big assumption. So this is an interesting formalism, and of course we go on, and I would come back to this somewhat. And as I said, so you need to have this is what I just said. You need to have an infrared safe, collinear, well-behaved factors, so that you can use this factorization formalism as we most of the time take this as granted. But from theoretical viewpoint, you need to prove this. And there, in fact, the Sakura Prize-winning works on this, like the Sturman, Soper, and Collins. So they established the QCD factorization for drill-YAM process at an early time. So it's very important, tedious, difficult work even to show this to rigorously, okay, to all orders in perturbation theory in the drill-YAM process. So it's for DIS. DIS process was proven, and direct photon is okay. Heavy quarks more or less okay. Only this finite number for processes actually. Okay, so let's go to this the factorization. We want to have the splitting behavior. However, if we go to the extremely high energy, the appropriate treatment is not the photon and the Z, rather each one of them has a separate the symmetry. Therefore, when you do the evolution, you want to do the renormalization, do the evolution and the parton, so on and so forth. You should do this with the symmetric the theory, symmetric phase. So therefore, you go to this unbroken phase, which means you don't identify photon and the Z, but rather the photon is the U1 part, and the Z is the SU2 part. So they're separate. So of course, eventually you can come back to mix them according to one angle mixing, but in terms of the consistent treatment, you need to do this so-called unbroken phase. So that's what we do. So it's the calculation is straightforward, and it so turned out the leading one is very similar to, this is very similar to photon. It's the same as the photon, what is the effective photon approximation or Williams approximation. This formalism you see it very similar, but this is the Z is energy fraction of this photon carried by photon. As you can see, when Z is 0, that's soft limit, so this is a soft behavior. And here the KT is transverse, and the KT gave you the log Q square. I said it's collinear behavior. So 1 over KT squared is a collinear behavior. 1 over Z is the infrared energy behavior. This is standard. Don't need to go over details, but of course you need to calculate the Higgs factor as a scalar in this case. But it's not much different. There's no infrared behavior, but it's a kind of a collinear behavior. This is the Yukawa coupling, chirality flipping coupling. So that's not much different from people's expectation. Then when of course you continue on to do the gauge boson self-interaction, this is once again identical to the gluon, and this is the new, but it's kind of anticipated without the infrared behavior, but with the collinear behavior. So then we went on and on. So then the other comes numerically. Do they matter at all? So here is one of the early estimates from to estimate the 100 TeV FCC, the one I mentioned at CERN, for multiple gate boson production. Of course, so because of phase, you have the capacity to do the multiple gate boson physics. So you can see that each additional gate boson is very perturbative from his calculation. Of course, he only used the perturbative calculation. Each one is very perturbative, additional electric coupling, and a little bit of phase-space suppression. So each one of them is almost 2 orders of magnitude down. Each additional gate boson radiation, roughly about that, 2 orders of magnitude down, 3 gate bosons, and 4 gate bosons, and so on and so forth. However, from my previous argument that the collinear behavior should be taken into account. In fact, the collinear behavior should be resummed many logs rather than this. That's what we tried. We tried to compare with a splitting here. If you count the number of gate boson here, the leading production, and 1 gate boson, 2 gate boson, 3 gate boson, and different counting, different suppression. You see that each additional gate boson, including collinear behavior, including the resummation, is not really particularly predicted at this. In fact, instead of 2 orders of magnitude, it's roughly only about 1 order of magnitude larger. So therefore, multiple gate boson physics and at high energies behave differently from your pure perturbative estimate. You need to treat this properly. This is one simple indication. Here is an interesting comparison. So we want to see, let's say the 2 gate bosons in high energy. Okay. You have a WZ production and be kicked by additional boost, additional jet, either gluon or quark jets. So 2 gate boson plus jet. And to see the splitting and behavior, and the splitting behavior is a collinear behavior I have been discussing, right? So here is the 2-dimensional kinematical plot. So here, this is a delta R is a separation in phase space and the rapidity and atomic angle, 2 gate bosons. So here, this is a transverse momentum of the W with respect to the transverse momentum of the W with respect to J spacing here. Okay. Now you see that the region here you have a lot of events here in the color here. That corresponds to pi, which means the W and Z back to back. Okay. Then the W has a large PT with respect to J here. So this is that region. But here is also interesting, but opposite. W and Z are back to back, but W is radiated with respect to the quark. So that's the low PT, the low PT between W and the J. Here is the region that the PT is spread out all over places, but W and Z are collinear. So this is the splitting part. Then we use the matter graph to try. Matter graph did a pretty good job in basically similar to this. Okay, so then if you compare with the existing the common packages like PTHEA missed completely. PTHEA does not have the collinear behavior into it. So this is the PTHEA output. The PTHEA output certainly gave you the the Z radiation part, gave you the W radiation part, but the collinear part, the collinear WZ part is totally underestimated at the high energies. At the LHC, that's okay. LHC, this is not 100 TeV, and it's only 1 TeV. This part is not the dominant part anyway, so it's fine. But so the PTHEA does not have this the electric splitting property yet. Only about a relative recent, I think maybe last year or so, and Peter Richardson of this the Hurwicke collaboration put this in, but they haven't been tested yet. It has not been tested properly, but the importance is recognized. If you really move on to the higher energy regime in the future, then all this the collinear behavior, splitting behavior should be treated just like a QCD rather than the perturbative treatment. I think that's interesting. Now let's get into the high energy electric physics. I mentioned to you about the Chris Crick, the comment that his comment was the first stage for this famous paper, right? The famous liquid cycle paper. Liquid cycle paper was the first one to consider, but it's considered electric sector at a very, very high energy. But that time, very high energy is Higgs mass. It's TeV, 1 TeV by that time. They were thinking 1 TeV was very high energy. Okay, but that was they calculate. They found that at a high energy, much larger than the W mass, the longitudinal component can be simplified as a scalar. So therefore, it's called the Goldstone-boson Equivalence Theorem. The theorem tells you longitudinal component is not necessarily a vector anymore. Longitudinal component is just a scalar component. The scalar remembers the origin, where it's from. That's kind of a trivial. Weinberg wrote down the theory before the symmetry breaking. And then we work on this. After symmetry breaking, we have W mass and the top quark mass, everything. And then you say, if this W mass is irrelevant, we'll go back to Weinberg theory. Of course, it's obvious. But you need to quantify this. To what extent this statement means anything. So now let's see that if you continue to ask the question, you see the inconsistency. So first of all, let's see. So you write down the longitudinal gate boson wave function. As I mentioned to you, is proportional to the energy, to momentum. Therefore, we call this bad high energy behavior. And there are corrections. The corrections is under the assumption that all the gate bosons are very light, massless, with respect to that energy. The equal sign means that this is 0. Otherwise, they are fractions. Okay. So that's the first thing. We call this a scalarization. Once you dot this full momentum into your matrix element, you don't have an index anymore. You kind of scalarize this longitudinal vector. Longitudinal vector scalarized into the Goldstone-boson, and that is a mathematical description of Goldstone-boson equivalence theorem. Okay. Now let's continue on to see what happens. Okay. Now, of course, it was argued over and over again, including the liquid cycle paper. Liquid cycle paper was a WW scattering, but immediately after that, and Chenoweth and Gaillard at Berkeley discussed about this top quark. The top quark may be heavier, but that time it was not too heavy, not 170 GeV yet. But nevertheless, top quark is the heaviest. You cover coupling, then you calculate the longitudinal behavior. You find that normally you have E, the energy. There's another energy, and then the high energy behavior is very, very bad. E squared over V squared. So turn out because of gate symmetry, this term doesn't exist, cancels out. But however, the surviving term is directly proportional to, linearly proportional to the energy. That's also kind of bad. It's also bad high energy behavior. You apply this theory to arbitrarily high energy, your value unitarity certainly is not going to be the consistent theory. What happens is really the Higgs mechanism. The Higgs mechanism restores the symmetry. When you have this the Higgs exchange into the place, and you put this longitudinal Goldstone-boson almost like into the Higgs multiplex, and they know each other. So then you find out that this high energy behavior is cancelled, is regularized by the Higgs mass. So this is a good-handed behavior. However, remember this was the early argument. Higgs mass cannot be arbitrarily heavy. If Higgs mass is arbitrarily heavy, you have the same problem for the high bad behavior. This is where the Higgs mass, along this line, and this is where the Higgs mass bound around the TeV was from the quick cycle the argument. So therefore, the high behavior need to be taken into account properly and treat this. But then you say the fermion is probably okay. So you say, so let's look at the massless fermion radiation. The massless fermion radiation into some longitudinal gated boson. Sure, you multiply this longitudinal gated boson into the matrix element. Remember, if this fermion splitting is conserved current, just like a photon, this is the multiply this into is 0. So there's no longitudinal splitting from fermions. But of course, we know there's the axial vector term, just like a Z has a actual vector term, and that's not 0, but that's proportional to the fermion mass. If that is proportional to fermion mass, the statement is that according to Goldstone-boson Equivalence Theorem, then the fermionic radiation of longitudinal gate boson must be 0, proportional to the fermion mass. We know that's true. LHC people discovered this the longitudinal gate, the fusion to Higgs discovery has significant contribution from VBF and significant contribution from longitudinal component as well. And what happened? Now the term I just mentioned to you, they missed. So this statement missed. So that is that this leading term is not leading term. Leading term is 0. Goldstone-boson equivalence theorem is not always valid if you count the higher powers, higher twist effect. In QCD, we drop them out, but QED you cannot, because that's turned out to be the leading one. You think there's a 0. So this was confused by many people for a long time. So it turned out that in fact that this calculation was carried out by Gordy's collaboration and the Sally's collaboration in the mid-80s. They calculated splitting at the splitting I mentioned. This is a standard splitting I showed you in the very beginning. This is the same splitting as the photon splitting, same splitting as the gluon splitting, pure gauge, no problem. But if you split the longitudinal, this is non-zero, but why is non-zero? That's what I want to explain this to you. So this is correct. This is true. Even consistent with our current LHC measurements, is there. VBF is there, and our longitudinal component is not negligible. You have to put everything together, so they do not vanish. So, but there's no collinear log. Why? And this is the interesting thing. So, because of this power counting, this power counting in the normal gauge theory is a small. We drop them. It's a higher twist effect. But if you keep this term, there's a factor. Instead of the pure gauge factor is the k squared over k squared, and that's the log. The standard log, the log is large. But there's a factor here because this v squared over energy squared is not negligible according to the Goldstone-boson equivalence theorem. But when you integrate this over the whole phase space, it is constant and a power law suppression. These are power law at a height square. And this is fermionic splitting to longitudinal part, and we gave the name called ultra-collinear. And indeed, if you calculate the longitudinal from that, we mentioned to you already, this is like that. You calculate the Higgs radiation not from the Yukawa coupling. Yukawa coupling is 0 because the Yukawa coupling fermions is 0, small, but the leading contribution is not from there anymore. And you can continue on to calculate the systematic calculations. But this is interesting to see the feature, but the general feature is that this one does not behave like a gate boson at all. The longitudinal gate boson does not behave like gate boson at high energy. And it's even not the Yukawa coupling. Yukawa coupling can be very small, but it's a higher power correction. So this is the statement you are necessarily taking into account the symmetry breaking effect. So this is called you need to do this broken case. Okay. So this actually is interesting that if you recall the history, in the QCD textbook by Keith Ellis and Jim Sterling and Brian Weber, There was a paragraph that I read, I did not quite understand in the beginning, and they said if there's a scale, power counting scale, like a lambda QCD, and Buchanan scaling is rigorous, Buchanan scaling is restored. Buchanan scaling, you know the Buchanan scaling, right? If you look at the parton distribution function, it seems to be only dependent on x, not the energy. But it turned out that is violated logarithmically due to QCD dynamics. So that is the log I showed you previously. It's the scaling is violated by logarithmic the evolution by QCD. But if logarithmic is not important, like this splitting, and Buchanan scaling is completely restored. The no log enhancement is constant. So they said this Buchanan scaling restoration. Now I understand that exactly what they mean, that if you keep this term, and if the log term is smaller, you keep the term, it's constant. It's no logarithmic enhancement. Buchanan scaling is more flat rather than the logarithmic enhancement due to the QCD dynamics. So
and this is the PDF, it's not the DTF, right?
Oh, I worked for DPF for too long, I guess. Yeah, right.
This Buchanan scaling restoration is actually the leading log statement, right? It's not
Right, exactly. If you include the higher orders, but leading log, it's a leading log behavior, but leading log resummation is like that. Yes, sub-leading log, yes, sub-leading log, you have other gauge bosons come in. Yeah.
And also just to interpret your result in the previous slides, yes, massless formula can emit a longitudinal double boson. That's a higher twisted effect, which means longitudinal double boson PDF is weaker than transverse double boson. Yeah. Due to this MW over E suppression.
The overall, yes, overall is, but it depends on the process. It depends on the matrix element.
Yeah.
If the matrix element comes, for example, you couple to Higgs, the Higgs.
There's a longitudinal enhancement for the partonic cross section.
Yeah.
That is going. The enhancement is going to be cancelled by this suppression factor. So there's no more PDF give you a MW over E suppression,
right?
And
right.
your matrix element give you E over MW enhancement. They cancel. No enhancement.
Yeah, I don't mean this is necessarily enhanced. It's process dependent, but this is the leading behavior. Leading behavior is not the gauge boson behavior. It's more like the scalar behavior, but plus power counting, higher power, the symmetry breaking power counting. Okay, so let me be quick and get into something. Again, this is the same statement, right? This is the same statement when you calculate the scalar sector, you find that the scalar sector is leading contribution is from this the symmetry breaking rather than the symmetric phase. So symmetry breaking phase is necessary to look into. Okay, let's be quick. Here is the numerical demonstration here. Here is the splitting. The splitting for this fermion to split into a fermion and gauge boson, and these three curves. Here is a massless approximation at high energy. If everything is massless, this behaves very much like a gluon or photon. But if you have the mass layer threshold, you regularize a little bit by this. However, the longitudinal splitting is almost like step function. Is this not logarithmic extension? This is almost like step function due to this behavior. Once above this the Q the high Q square, that term dropped like a power law suppression. So this is almost like step function. This is a different way to show this. This is over the energy fraction. This is similar. So this is a very long tail extension, logarithmic, and this one is very narrow in this small region, and we call this ultra-collinear. This is basically the scalar behavior, ultra-collinear, always within this region. And so turn out this actually it's very important phenomena. So this is the kinematics for the so-called the forward jet tagging and the central jet vetoing. So the jets, at the LIC, you tag the forward jets, and you don't want to have the too many central jets. Of course, QCD also gives the same behavior. I simply ask the electroweak. So if you think about longitudinal physics, longitudinal gauge boson physics to couple to Higgs or anything in that region, because at ultra-collinear, you tag the forward jet. The jet is very, very forward there. That's where the jet tagging actually the kinematical foundation is from. You tag the forward jets, but if you look at the jet all over places, it's a fewer and fewer, but it's spread out all over places because the transverse gate boson splitting. And you don't want to see too much in the central region so that you can purify your Higgs signal. So this is the foundation for this the central jet vetoing actually at early time. So this is this kinematical reason for that. Okay. So so this is so sorry, I worked for DPF for too long. I always write for DPF. But anyway, so this is that feature. But this feature is also interesting if you see the high energy splitting. If you have extremely high energy electric physics, you say if you have a TeV, 10 TeV scale Q squared. Let's use the W prime as a representative, but it doesn't have to be W prime. It's just some energy, new energy scale. And then this has a star splitting. But you can see because of splitting, this is just which one is the solid curve is the whole story, including the soft region here. But this is basically Brad Wigner. The dotted one is a simple decay, no showering. But then you can see that the heavy object can split into another W, and this is almost like an electric jets. Electric particle going forward is a bunch of particles, including multiple leptons in multiple gate bosons, Ws and so on and so forth in it. But each one of them certainly has an order of 10–20% contribution. But this is necessary to take into account. So therefore, you can think that to some extent, the electric farnesyl particles, almost like QCD particles, because of color splitting. Then even any electric particle, even a neutrino, will easily radiate a W to change the identity, radiate another Z to change the identity. So neutrino itself is not like a low energy, it's missing a particle anymore. At high energy, all this the jet evolution will come in with a predictable thing. So neutrino will be multiple particles in the final state with the well-behaved and gate boson radiation. So it's basically at high energy. It's just this is a kind of a analog to the QCD phase transition restoration. You restore this the symmetrical phase, and then all these the fundamental degree of freedom, like those particles, and they will convert into a bunch of particles altogether. So this is another plot to show the splitting. This is a splitting into W. This particle, these labels are the parent particle. B gate boson, Muon, and the W minus to radiate to fragment into a W plus in your state. So here is the full energy jet. And here is the other jet is soft, so there's a soft similarity. You can see that whenever you have a both end, that is basically the gate boson splitting. You have both one of the particles is soft, the other one is not, or other one around. So you can see this. So all these particles would shower into something else. Now let me get into the unknowns. These seem to be important. And of course, you want to do all order resummation to take into account the higher powers. But actually, it's highly non-trivial. The reason is that let's consider the electron radiation. Electron is your high energy beam to come in, and electron radiate the soft W, the soft radiation. When this soft W is very, very soft, it's almost like an infrared divergence, and you need to calculate the one loop correction to cancel that. So that's a standard process. You calculate the one loop correction to make this the soft W to cancel this in. They don't cancel. This electron coming in, neutrino coming in. You never have electron coming in, something else coming out at one loop. So they won't matching. They won't have the same matching diagrams. Why is that? The reason in comparison with QC is that we are demanding explicit gauge quantum number, SU2 quantum number, either electron or neutrino, rather than it's equivalent to demand color for SU3. You never demand to observe a red color U quark because you sum over them. They are unobservable. You sum over all of them. Therefore, this is the theorem many theorems. And for example, Lee-Nomberg-Knuschitz theorem tells you sum over all the degenerate quantum states. It's basic quantum mechanics argument. You sum over all degenerate states. There's no infrared singularity in our real world. Okay, so but you need to sum over all degenerate states. Otherwise, you break that. You break unitary matrix when you insert that. And this is called this is more explicit. You see this way. Look at the splitting, electron splitting neutrino, and neutrino splitting electron, and this is splitting, and you have this the infrared divergence here. But if you calculate the virtual loop fraction, you calculate loop fraction, you include both electron loop, electron final state, and neutrino final state. You need to sum over all of them. You need to electron and neutrinos are not observably separatable at high energies. Just like if you demand this is similar to what I said there. Neutrino will split into different other final states, including electron. So in a non-perturbative sense, you sum over all these things. Is neutrino demand neutrino to be a neutrino is ill-defined at very high energies. Just similar to that, you demand a colored quark. You cannot demand that once you're in this energy regime. So you sum over this, they cancel out. You sum over all these ISO2 quantum numbers, similar to ISO3 quantum number, the colors, and you have this will-behaved behavior. Otherwise, there's no leading log is okay. The second leading log, the sub-leading log is incomplete, the cancellation. This is called the Bloch-Nordsieck theorem violation. The Bloch-Nordsieck theorem is even earlier than Lee-Nomberg and the Knuschitz theorem. And that was the early time to see why the photons, soft photons should not be divergent. Soft photons all around us. Once you sum over all these degenerate states, you regularize. So then this part, of course, there were a lot of argument how to do this. And Christian Bauer company, Mendenhall company, they use the sketch. They use the sketch formulation to resum all this, and then they can they claim you can restore this sub-leading log cancellation. So basically, what you need to do is you need to define a sufficiently inclusive process. You cannot demand exclusive. You cannot demand to have a neutrino forever at high energy. Neutrino will radiate infinitely and to change the identity. That's called sufficient. This is an inclusive process. Inclusive process is necessary to regulate this, but it is even not sufficient. Sufficient thing is that you need to define observable, more than just the process, more than just cross-section formalism. I want to see the transfer of the momentum of such particle, such state, and that is the observable, and that observable will have to be safe for the infrared and the collinear. So that was the theorem that I mentioned, this Sacra Prize winning theorem that Colin Sturman. They showed some observable that is a sufficiently inclusive process and also well-defined kinematic observable. And that is good. That is not complete done yet up to this level. But you can admit a defeat. You can say, well, I'm not calculating not accurate up to this level. I introduce double mass. You introduce cutoff. That's regularize your cross-section, but you cannot demand your cross-section is accurate to sub-leading log. But this need to be taken care of properly. We think there are ways to do that. We think we can handle that maybe in the near future, but it's things like this are not totally done yet. I'm basically done with the overall theoretical discussions for the interesting phenomena and the conceptual and technical difficulties for the electric sector at extremely high energies. But that's it. But the rest is the example. I will be really quick. So this is an interesting example. It's a lot of work has been done along this line. It's a recent excitement, right? Just because of the possibility to build the lepton collider at the multi-TeV. So that's just a fantastic opportunity for us. So then we apply the electric formalism we discussed there into this the application. We know that the map collaboration and also the mice collaboration. Mice collaboration is ionization cooling experiments, and we know that the mice collaboration moved from Fermilab to Rutherford Lab in the UK, and in the past few years, they demonstrate they experimentally demonstrate the feasibility to do the successful muon cooling. And the acceleration technology seems to be so well developed. Once you have the beam, the acceleration to 100 GeV or TeV is not a bottleneck. That's not a problem. The problem is the high quality beam to begin with. So microsecond muon lifetime, and then you want to effectively accumulate the muon production is very efficient. You just do the proton on the very heavy target. You do the proton on very heavy target. You generate a large number of the pions. The charged pions will decay to muons 100% basic. You as many pions you produce, as many muons you have. Muon preparation is not a problem, but they spread out all over places. And you have to, they call it a 60 cooling. The 60 cooling is positions and also the momenta as well as the time. You have to line up at the right time to go. So it's 60 cooling is highly challenging. But this demonstration is good or not good enough. It's good that you see that technically you can do this cooling to cool this one dimension notably. But this is not too big. It's something like 80% only, but you need order of magnitude. You need 5 orders of magnitude cooling. It's a long way to go, but they claim, our accelerator colleague claim that there's no showstopper as long as we put enough effort, enough money, and so on and so forth. So we accept that word. Okay, we'll be happy to accept that word that in the near future, we may be able to have sufficient cooling to have a high quality people. This is another interesting idea. I like that. Yeah. No, it's a very, very weak. This cooling is something like 20%.
Is that a linear plot and they've gone down
less
than factor of 2?
Even less than factor of 2. From 2 to 1.65, from 1.9 to 1.6.
You're supposed to go 5 to 6 orders of magnitude.
Yeah. Well, we can do 1,000 of them. This is only one of them. Okay. But we have 1,000 of them. I have several combined. The arguments, they are arguments. So when I further look at it, in fact, even more active than that. Some colleagues said, "Oh, this is exactly from my simulation. That's a Jackson physics. Why is it surprising? It's from Jackson physics that you can predict it, you can plot this. But of course, I think it's important to demonstrate. Yeah, the Jackson physics can be implemented. So I think that's significant. And this is basically how this new excitement started. It was 2 years ago with the Nature paper. They demonstrated the real cooling effect. To some people, it's not surprising. To us, I think it's very it's a proof of the principle. Yeah, it's by far. Yeah.
The sequence. Another issue that I recall was the problem was the huge neutrino. Yeah, so there's also significant problem. But of course, you have ways to do angle and shielding, many things. But so far, from our accelerated colleagues, they claim that they have been able to design certain things to be safe up to 10 TeV or 14 TeV. If the muon collider reaches the center mass energy around 10 TeV or 14 TeV, the neutrino radiation hazard should be more or less under control. That's a statement.
The neutrino hazard will be more like
under control. Sorry.
Under control.
Yeah. So if the machine energy is not higher.
Right. This is off the site. The radiation of the radiation of the strong neutrino. Right. So,
hitting on the environment, hitting the surrounding, and you detect it's almost like, as we know, it's almost like energy to the fourth power, something like that. So that the energy is really. So honestly, you're right. This used to be one of the 2 or 3 major concerns. It's an environmental issue, and you cannot handle. And the more shielding you have, the more material there is, more collisions. Yeah. But our accelerator colleagues said this is it's manageable. Yeah, I think this is interesting. This idea is also pretty cool. I don't know how far that makes it realistic. Yeah.
They didn't book a class, but they are value
okay.
Undergrad.
Yeah. Okay. Yeah. Okay. So we stop here. So we just summarize. Okay.
Although we are very excited about real-time, but you probably have to.
Yeah, my problem, I always run over time, in particular for the last part. The case I want to give you one punchline. Of course, we implement everything consistently. So far we are one of the first ones to have implemented everything consistently. And let me make the interesting punchline for this. This is what I want to say. Muon collider has this capacity to be like an E+- machine, so that you have the energy threshold. You can reach energy threshold to produce heavier particles twice as much as that one. And then you have these splitting functions that we calculated. You have both the proton-proton, like proton-proton, all from the PDFs. And a very broad spectrum. Any particle resonance, E prime, W prime, you pick up from this PDF. And Muon collider had this capacity because of radiation I mentioned that we established, and also had the direct annihilation, just like the +- collider. So this collider is pretty cool. I think it's very interesting to put forward. Okay, so a lot of details, and we would not comment on the Higgs measurements. We better than anything else. Any threshold, and the next one, dark matter source. Kinematic is very cute. Kinematic is very different from the proton-proton as well, because you know the initial state so well, you can measure the missing particle mass. Okay, so that's.
I think I will coordinate with them.
No, so I can finish in 1 or 2 pages. Okay. Okay. Yeah. So of course, I was kind of very rushed to skip quite a few things. Let me recast. The Muon collider has a capacity to reach the energy frontier, to do the direct annihilation to produce heavy particle pairs. So okay. So that's very important, and because of the collinear radiation, and you have everything is parton. So this what I skipped, unfortunately. So everything is parton. Here, any particle in the center model, W's, bosons, quarks, gluons, in the leading order, muons of course is there. But you have a neutrino. It's a like neutrino collider, because a neutrino is only soft W radiation. Neutrino carry most of the energy. Unlike the other particles. Muon, of course, carry most of the energy, but with a soft radiation, I argue about soft radiation. Soft radiation W is not very energetic, but it flip into neutrinos flavor. This is not only the muons carry the majority of the energy, these are diffusion. Neutrinos carry huge energy too. But when the neutrino scattering will generate new physics, that's the way they give me a model is okay. But it's cool, right? You have the muon collider, muon collider. You have the neutrino collider, high energy, not low energy end, not like photon. Photons are always low energy, soft. But neutrinos are high energy. So it's very rich physics in it. So it's pretty cool. So let me since I rushed here. Oh, here is the 1 by 1. Buy one, get one free argument. Here's the threshold. Muon annihilation carry the full machine energy. But all these other beta bosons will carry soft energy. You can separate them out kinematically. You can when you produce new particles, such as TT bar, and you can separate them out to see the different contribution, different channels, and so on and so forth. So you really have the good kinematics. The last good, this Higgs position is a skip. So it's obvious you produce more Higgses at this collider. So then that's obvious. I don't need to say anything. But here is pretty cool. Because of the well-defined beam energies, U plus U minus, similar to E plus minus collider, unlike proton-proton. Proton-proton is parton scattering. You don't know the parton scattering energy, but here you do. You know, U plus U minus. Suppose you observe some particles in fantasy. Even you observe one, you observe single photon, monophoton, and you reconstruct the recoil mass or the missing mass. The recoil mass you even don't need to look at, because this kinematic is so well defined. All the other masses will be lumped into this one. Suppose we're looking for dark matter. We're looking for dark matter in the massive dark matter wing, my favorite. Sorry, Prisca. So there are the other important dark matter candidates as well, for sure. But here, if we look at for the wing dark matter, this missing mass is unlike LIC. LIC is missing kinetic energy. if the missing mass is insensitive at the LIC experiment, LIC experiment is only for missing kinetic energy, but here it's invert mass. So then suddenly, if you have a particle 3 TeV, these missing mass, these are 3 particle, 3 TeV particle are gone. Now we even don't need to observe. As long as you observe 1 particle, they can start wave is the cutoff. So this the electronic collider has this well-defined kinematics to go way beyond the access. Interesting features, quite a few along this line. But let's this is the one that the Jen and the company we studied to see the improvement. So here is a high luminosity LIC will be able to reach 100 GeV WIMP, like a SUSI-like, but then you go all the way to the Muon collider and the FCC and so on and so forth. A lot of papers, a lot of excitement. It's even incomplete list. If you are interested, there is a SNOMAS, what it's called. It's called Muon Collider Forum. I mean, there was a Muon Collider Forum document to update many other things and list many other things way beyond what I said. So let me just the recast what I'm thinking about. Even before Muon collider, I was always thinking how we can systematically understand the electroweak sector at a very, very high energy, way above the electroweak symmetry breaking. How do we do the power counting? How do we compare the so-called Goldstone-boson Equivalence Theorem, and how to specify the electroweak charge? Unlike a QCD charge, we cannot specify. It's even better. Here, you specify electroweak charge. You call the electron versus neutrino. There are subtleties if you want to calculate this. Calculate theoretically order by order. So there are many issues. Whether we can introduce a perturbative cutoff, how the longitudinal is like a scalar, how the scalar is like or not. Chirality, fleeting thing, you cover showering, ultra-collinear, and quite many issues, even including theoretical formulations. So I'm done. Yeah. And you need to know this first before you think about the beyond standard model physics. Just like you need to know QST very well before you search something, deviation, something. So 100 TeV collider will be relevant. Multi-TeV is a new excitement, extremely high cosmic ray. There was even a very cute paper by Nick Rod and Christian Bauer. They apply this formalism to extremely high energy. Clients may be interested in this. Extremely high energy region, the showering. You may know that paper, right? It was a very nice parallel paper just 2 years ago. Just 2 years ago, the extremely high energy shower, it doesn't behave like your simple estimate. You need to do resubmission showering. So once you get to the extremely high energy regime, all these things will show up. And that's still a theoretical issue to understand. Even after so many years, the Chris Quick said they worked out the electroweak at high energy. I think it's still interesting. Anything fun. Okay, thank you.
Let's talk about
so this cooling thing where you said you get the 50% or something, not even factor 2, and you said that's okay because you can have hundreds of them or thousands of them. Yeah. What does that mean in physically? What do you? Just
more money.
No, but
so you do many times. You do many components. Even either parallel or
yeah, but many components. How many can you have?
Oh, they claim 1,000.
Yeah, but you need like 100,000.
This probably is the early demonstration. So it was okay.
But even 1,000, is that feasible?
Yeah, so I cannot defend because I did not understand the every step, but this is written. This is clearly written as a statement in our SNOMAS rating.
Okay.
I'm not making this up. I'm quoting our the accelerated colleagues rating. It's a SNOMAS report.
It's still a relativistic particle. Use the energy point to compress the transverse momentum spread.
Yeah, but there's something physical that you're having to do, and does it make sense to do it 1,000 times?
Yeah, it's ionization cooling pass through the charged particles through the gas,
right.
through the interactions you reduce the momentum, and you reaccelerate them immediately. in the longitudinal direction.
Okay.
And they think they can do a subtile. In terms of physical size or accelerator.
Well, there's the question of physical size.
Yeah,
right?
physical size, people say, well, they actually talk to us about the size in the KITP workshop. I think it's 1 kilometer. You need 1 kilometer.
Okay, but for 1,000 of them.
Yeah.
And now to get 100,000 of them?
For the, I don't know the number, that's the accelerator design. They say a kilometer of the initial cooling is that's what they have in mind. So how much does the velocity change like after one of these modules?
That depends on the demands of quality, the beam quality. If you can tolerate the water and the spreads, you probably accumulate more. One, the Higgs factor is at early time in Gen I, we work on Higgs factor to really hit the Higgs resonance. There's a high demand for the quality beam. And any spread will have to be a few any, which of course is durable like the lab can do any for electron, right? So it's concealable. But then copy the mass orders. It's a trade-off. Okay. You don't care so nowadays I think I care the energy expression.
Yeah, so like after like 1,000 of these modules, do I get any velocity back?
I think the person who answered is the Scottenberg from LBL, and he basically said it only 1 or 2 orders of magnitude lower
After 1,000.
After the he said it's not good. He's not good, very bad already. I don't think that 1 order of magnitude, 4 order of magnitude, it's not going to change your physical discovery very much. And it's threshold. Look at IC. Once you try IC in the very beginning, you get 17. Things pop up.
It took a little bit of time to figure out. But actually, on that point, I wanted to say that. So I think when there was discussion about the whole thing on beam structure, right? You don't really have electrons which fly in the positive. You have an electron and a photon or a radiated electron, and the actual energy, the spread of the energy is enormous.
Yeah.
So what would it be for this machine?
It's fantastic. This machine is fantastic. So the energy to the whole power behind.
So still you got a lot of energy there.
Yeah, but it's and
for the distribution of clicks. So yes, of course. But the actual radiating process will other very energy. So that gives you fixed beam spread. It's still really a nice delta.
You're absolutely right. That's physics there. The two reasons is better. Obviously, we all scale with the mass, right? Electron mass and muon mass is 200 times full power. You immediately get 5 order of magnitude less radiation than the possible energy. So that's a first thing. Second thing, we're doing the circumference. Then it's a linear. Then it's a linear has both the intensity and also the beam travel. Then it's very, very nice.
No, the beam, right, the beam.
But this is the circumference. Circumference, you don't need to make the beam that high. Linear collider, you have to make the really, really tight. Only collide only once. Separate ways. I really shouldn't have said. If you collect the separate ways, you I need to so much. Yeah, gone. But this one, the thousand times. This one, once you have the gamma factor, relativistic gamma factor to enhance the muon lifetime, the 3 or 4 orders of magnitude. You can circulate even this lifetime at the short at the rest at the 2 microseconds, and you can circulate these muon beams a few thousand times, and to 10,000 kilometers, even more than that. So even the relativistic beam, it is conceivable, and radiation is to go better than that. And so the man I just trying to answer one question that they claim if you can sacrifice the energy, the luminosity, sorry, what I'm trying to say, they can do the energy spread up to energy. Few energy.
That's what they're saying.
Yep. But of course, sacrifice the luminosity by more than 92 or something.
Oh, this is going straight. You mentioned straight here.
Yeah.
Okay. That's a very fine combination.
Yeah.
Roger, you referred to click in the past tense.
I was a reviewer.
Is it finished?
Well, I have no idea. It's no, it's, I have no idea. I mean, everybody was reviewer, and I just was responding.
Click will be.
Sorry?
You said click was. As opposed to click was, it may still be.
No, I mean, certainly the beam for the highest energy region, the very high 3TeV version, when the beam strong is enormous, and to recover it. So I don't know, just one of the extent. But you have other very serious detector problems. You got a lot of background.
That's the third thing. Brian mentioned about the neutrino header is most difficult one. And the back thing, the back means you mentioned that probably the second worst. It's called bit.
Yeah.
Beam induced backward. Unlike the electrons or proton, you decay constant. This split over part of the whole into the detector. Because they induced backward. That's because they define the forms, the scales, and so.
Given all these problems, and what's the renewed interest in it? I mean, in a sense, are there plans to do this in the US or?
Exactly. So if you did not get a chance to say that, so the formula people, not officially, but unofficially, like the leisure reading, and they plot this. They call it side view. They use the currents to estimate to fit the collider rings inside formula. And they even play, even simply using the existing parton ring. They may be to reach the switching collider already. Without thinking about other problems, we use other things. But they simply look at the energy, the energy accumulation, they may be able to reach roughly switching the existing parton ring. And then they plot this to all the way up to the border for the left sides, not bother our neighbors, and they can go to 10 TeV or slightly if they make the ring bigger. That's the point. I think the point is
this money being given.
Not only money, but even though I have so far, I think the P5 comes to come.
This is what big arguments going on now is asking for project. Maybe even a t-shirt.
Yeah, they have very nice t-shirts. They must have one. I don't have. They didn't give that to me.
I didn't buy it. Sell it to me. That's why I don't.
That's all. That's the only t-shirts to raise money.
I think the young men really got excited about this possibility. Possible that we can play a significant role. We here in on US soil.
Yeah, it could be so that this is probably not the next FCC. So FCC, if they're right now talking about 2043 or so 5 years up to the end of the age, which may sound terrible, but actually we're 5 years up to run 2 of the other FCC. We're still deeper than that. 5 years is more than that. But that's sort of 2043. The idea is this can happen in interim. This is a precise on the touches already there, and it's sort of a great site. And the FCC you have to draw. You have one detector in the hand, and another one in ANSI. So it's like who gets the logic for this is it could be done on a reasonable time scale and on a reasonable budget. That's at least the argument the thing managed. I'm sure there'll be lots of people in the some of this all about.
Oh, right. Okay. Yeah.
I was in that.
The radiation, I always wondered, this, the strategy that astronomers use for radio astronomy about putting something in a round valley so that it's protected. What about doing the opposite? So put it in a round valley whose radius is just the right, so your fighter sits in there and then all the radiation just goes into the walls. I mean, is there a site? Do people ever talk to? I think they usually think, oh, we should put it at Fermilab, or we should put it I know, but that's why I'm talking about it. It's the wall around it and just going over the mountains.
Well, we have to make it very big.
Natural, like in the mountains. It's a big, big radio telescope.
It's only been in an eye, don't it?
Yeah.
We were talking about this one, the other. I don't know the advantage, disadvantage. If you build a set with a lab, we know how hard we lost. Know how hard make this
greenfield site. Yeah.
What would be the radius?
Oh, I mentioned that it depends on the flower design. The people start now. Well, I can even show you. It's called formulated figure. We did formulated site. Just a few formula tampon rate is 3 and 6 kilometers. It's one kilometer.
There, the hazard for people is a much more severe problem.
That's true for the so that's true. I think it's still pretty far for this actually realistic composition, but the major concerns that we brought up, Roger, and there are key issues with demonstrating the first, and then it's not going to be needed. Now these people on this. It's probably next P5 will be lucky if the next P5 can consider this issue. These now, Roger said, very nicely summarized. It's interesting. We should put some significant R&D.
But I loved your insight about getting to do all, buy one, get one free. I do because of all of the collinear stuff. I never thought about that.
In fact, this is very rich. Physical is pretty rich. I think physical was really nice. But to the related aspect is some of the young stuff. Let's go and I can calculate this in a few days. But it's going to be 20 years to really have this realization.
Okay, do we have other questions? Well, I think we can continue a discussion on many different interesting aspects. Second part of the
Right.